We're TG2, and this is our presentation for the forward mechanism analysis and the synthesis of a slider crank. My name is Jorge Larrarte, and this is Jonathan Hibbs.
So we were given two mechanical applications to use, the 4-bar and the slider crank. For the 4-bar application, we used the windshield wiper. We followed this after Trico Products, who is one of the world's leading manufacturers of windshield wipers. And they've been in service for 100 years of manufacturing. For the slider crank, we utilized the steam piston engine, which is utilized mostly at the Walt Disney World Resort Railroad. We start with the 4-bar analysis and animation. We were given two sets of values that were already fixed for R1 and R3, and also a point S, which was given at an unknown location which we had to find. We followed these sets of equations that were given to us in our robotics class, which gave us theta 3 and theta 4 to determine our angles. We plugged in our own set of variables to be able to determine the mechanisms, in which we came up with a type 1 mechanism double rocker. When we plugged in our values, though, we came up with an error in which the system ran into singularity. It kept giving us improper values, which means the system wasn't working. After many trial and error, we finally came up with the correct, not the perfect, but the best set of variables to use, which gave us a type 1 mechanism crank rocker. When we plugged these values in, we came up with a better set of variables with no singularity occurring. For determining our angular velocity and angular acceleration of our points, we used these 4 sets of equations which we derived from our classes. When we plugged these set of variables into our Excel equations, we came up with a clean set of variables, again with no singularity occurring in these variables. For the point S bar, I take it over to Jorge.
Okay, another requirement of this project was to calculate it or to trace the position of the point S of the coupler link along the input variable. It must be noted that the point S data was chosen by the team from the initial parameters offered to the group. These two equations were used to calculate the coordinates. Here you can see once the kinematic analysis is performed already and no singularity is shown, we get a clean set of data. And there you see the closure 1, the trace of point C for closure 1, and the trace of point S for closure 2. Here are the analysis of the results. The angular velocities against the input variable. They cannot look similar except for the spike over there. These are the angular accelerations against the input variable theta 2. They also look similar as well. Once the kinematic was done and points S was traced, the team went ahead and animated the motion in SolidWorks, and the result was pretty similar to the plot obtained for the point S. This is a real life application. As Jonathan said, we chose like a windshield wiper. This motion is given by the link R4, which of the over mechanism, which gives the oscillating movement for a rocker. Now Jonathan is going to explain the part 2 synthesis of the slider crank.
For the slider crank, we were given 6 sets of variables, A1 and A and B points, with 2 sets of coordinates along the XY axis. We plotted these coordinates in an Excel spreadsheet. As shown here, we have position 1, position 2, and position 3 as shown for the points A, B. To determine the center point A0 for all these points, we use this set of equations that were given to us in our class. We ran these calculations through along with the length, determined the distance parameter as determined in our class, which gave us the position of A0 as well as the length of R2 for all those points. We also had to determine P12, P13, and P23 for the points along for these points along the axis of A and B. We had an arrow position with P23, which we had to find the image pole position for that point. To determine this, we use these sets of equations as shown here. These are the formulas that we obtained from these equations, as well as the final points for the pole positions for P23 and P23 on X and P23 on the Y-axis. We also determined the circle, find the circle for the slides that passes through these points, as well as the image point. Using this set of this equation given here, we were able to determine these points as shown. We also had to find the point C in the circle of slides. We used a singular point XC to determine our YC. Because of the plus or minus sign given here in this equation, we came up with two different variables. For our presentation, we used -8 for Y. We also determined the local coordinates of point C for the first position. Using these set of coordinates, using these set of equations, we determined these set of coordinates for theta 1. From these two sets of equations here, we were able to derive theta 2 and theta 3. Theta 3 was shown to be at a different position from the other two equations, so we added 180 degrees to theta 3 to give us the correct orientation. Here you see the set of points followed in a line format. This would be the following of a slider crank mechanism.
Yeah, as Jonathan said, this from the calculation before, we see like point C1, C2, and C3 lying in the slider line. So once all the calculations done, the team went ahead and calculated the parameters R3, theta 1, R4, and theta 4. Because the input variable is theta 2, the only variables that we need to calculate is R1 and theta 3. This was done by deriving a loop equation. As you can see here, from the first iteration, we obtained singularity on the calculations. And the team went back and checked that the position of point C2 wasn't between point C1 and C3. Beta 2 must be a value between 0 and 1, which is between the values of point C for beta 1 and beta 3 of the position 3. After several iterations of 1 inch incremental steps, we found out like a suitable set of positions for our mechanism. This is the redefined position of the line AB. This is a new slider line. This is a straight line, and the point C2 is between C1 and C3. There you can see the updated parameters, which lead to a clean set of data for the position analysis. The velocity analysis for the slider crank and the acceleration analysis for the slider crank were also calculated using the equations given in class. And the final result was a clean set of data also for the kinematic analysis, you can see here. An extra effort was to calculate the position of point B and calculate the coordinates of this point in order to trace it and to get a plot to comparing of what we're getting in SolidWorks. The final result is like this is the point. This is point S, or the point B that we were given at the beginning, and it's kind of like similar of what the plot that we obtained from Excel. Also, the circular motion here is smooth, so it shows. Here you can see that it shows like there's no dead position, no singularity. This crank always goes without stopping at any time.
In conclusion, using the synthesis of mechanisms, we were able to determine firsthand and beforehand if the mechanism would work accordingly before we even ever designed it. This would save a lot of time and money as well before any system is ever designed. Thank you for your time.
Thank you.
Look forward to it.